You're rushing through the grocery store, grabbing the essentials, when you spot a display of tortilla chips right next to the salsa. You weren't planning to buy salsa, but you toss a jar into your cart anyway. That pairing feels completely natural. However, the decision to put those two items exactly 6 inches apart rarely comes from a manager's intuition or a lucky guess. Retailers rely on uncovering concurrent purchasing patterns. These are statistical relationships buried deep inside millions of daily transaction receipts. To find those patterns, retailers treat the supermarket floor as an unstructured mathematical puzzle. A typical modern supermarket generates hundreds of thousands of individual receipts every week. Manually cross-referencing every item in every cart to see what sells together is a physical impossibility for a human team. This geometric diagram illustrates the core of the problem, the curse of dimensionality. With a small handful of products, the number of possible combinations is manageable. But adding even a few new products exponentially multiplies the number of possible pairings, creating a web of data so dense it breaks traditional analytical tools. To shortcut this computational roadblock, analysts rely on data mining, specifically a category of descriptive algorithms known as association rule mining. The most utilized tool for this job is a mathematical filter known as the Apriori algorithm. Apriori is an unsupervised learning algorithm. It doesn't start with a target, like trying to predict a sale. Instead, it wanders the raw data, finding hidden structures on its own. To make sense of the chaos, this chart shows how the algorithm applies its first statistical metric, called support. Support measures the raw frequency, or probability, that a specific grouping of items appears together in the data. The algorithm immediately discards combinations with low support scores. If only 2 people out of 10,000 bought a laptop and a watermelon in the same transaction, the algorithm removes that pairing as statistical noise. This progressive elimination leaves a refined collection of what are known as frequent item sets. High support proves that a combination isn't a coincidence, but frequency alone does not make a pairing a reliable predictor of future behavior. This is the second metric, confidence. Confidence tests the conditional certainty of the item sets that survived the first filter. It calculates the directional probability of an if X then Y relationship. It determines the percentage chance that if a customer already has item X in their cart, they will also buy item Y. Even when the math produces a high confidence score, the outputs are routed through a knowledge base subsystem to filter out trivial correlations. The knowledge base holds domain-specific rules. It identifies that a customer buying bread is likely to also buy milk and discards those obvious patterns. This forces the system to focus on the non-intuitive associations that managers often overlook. Passing millions of receipts through these filters converts raw transactions into a statistically validated association rule. The final output is an association rule. For example, it might show that a customer buying a laptop has an 85% probability of also purchasing a wireless mouse. This a priori process is the engine driving the broader knowledge discovery in databases pipeline used by global enterprises. Supermarkets apply these insights to rearrange floor plans, optimizing aisle layouts and bundling correlated products together to trigger additional sales. This exact same descriptive algorithm scales to the digital world, powering the frequently bought together recommendation engines of e-commerce platforms. That salsa purchase aligned with a probability curve a server calculated months before you walked through the automatic doors. While individual shopping choices feel unique, algorithms like Apriori demonstrate that consumption follows consistent mathematical patterns.